This is, I wonder if you just about make it out there. This is Holy Cross mock, and this is component 2 mock and paper 4, and we're on the last bit, the last leg, the essay. And we are presented with some information. Cyanide is a poisonous substance, and you know this because you've done the respiration topic, and you know that this has an effect on respiration. You've met this previously, cyanide, as an example of something that stops active transport as well. So you recognise cyanide. The actual clover plants themselves you won't have heard of, unless you've done Holy Cross mock number 2, I think, where this section is more or less the same, which goes to show if you do enough questions you meet the same things again and again and you become more comfortable with them. This bit's different, so they were obviously just a bit lazy and had ripped off this bit and then came up with some more. That's examiners for you. And we need A to turn the precursor into linamarin, and then we need the L allele to turn that into cyanide. Okay. And some more information. So this is in the leaves. This precursor, and this causes the release of the enzyme. So when the cells are broken, the enzymes are released, and that sets off the reactions to turn the precursor into cyanide. Okay, which coincides with it being eaten or in cold, the cells being broken. But really, being eaten, something munching on the plant will release its enzymes and cyanide, and presumably the slugs don't like that. And we've got some data, some mysterious part of Europe, and we've got a temperature, so cold there, hotter anyway, down at the bottom 10 degrees, it's probably hot for Manchester. And a strange little set of symbols, just these ones down here are cyanogenic. These ones up here are acyanogenic, and the ones in between, the proportion, these in between, kind of half and half, if it's like that, half and half. Use the information, okay, to explain which genotypes will lead to clover plants producing cyanide. Okay, so genotypes. So this is our kind of first cloud. Genotypes. That's definitely just an over there. Golden rules of genetics. We have got 2 copies of each. We've got 2 copies of an allele in an adult. Okay, so a normal cell of a plant will have 2 copies of each gene, one from each of its parents. And we've got 2 different genes here. We've got A and L. So our first golden rule is that we have got 2 A's and 2 L's. And you could list all of the possibilities. And let's just give you some examples. So to make cyanide, we need a big A and a big L. So we need the dominant there. And so, for example, big A and anything. So big A and big A, big L and big L will give us cyanide. Big A, big L, little l will give us cyanide, because we're making the linamarin and then that's getting converted. And likewise, big A, big A, big L, little l, big A, little a, and two big L's. They'll all give us cyanide. As long as there's that dominant big A or big L there together, they're both there, that's going to give us cyanide. So we're explaining that in a diagram or in words. If we've got two little a's there, then we can't make our linamarin. So cyanide, no linamarin, so no cyanide with little a's. And it actually doesn't matter whether it's big L, big L, little l, or two little l's. It doesn't make any difference at all, because if you don't make the linamarin, it can't then get converted to cyanide. And we've got another situation where we've got two little l's. We need a big L, dominant L, to make cyanide. If it isn't there, it doesn't matter how much linamarin we've got, it can't get converted. So, for example, any of our genotypes here. So, two big A's. Yeah, we can produce linamarin, but it won't get converted. So, in this situation, linamarin cannot get converted to cyanide. So even if we've got heterozygous there, so two little L's, it ain't going to happen. No cyanide is going to be made. And of course, if we are entirely homozygous recessive, we're not making the linamarin, and we also can't convert it, even if we had it, but we don't. So that's our, absolutely no chance of cyanide at all. So that's what you are coming up with in your first sort of area, and in beautiful flowing prose with labelled diagrams. The second part, fully explain the distribution of cyanide and acyanogenic and cyanogenic plants on the map. So you could do this kind of separately. You could go cyanogenic, acyanogenic. So there might be there's some differences between them. And fully explain the distribution. Well, what is the distribution? We get cyanogenic, so dark, kind of mostly dark circles, where it is hotter. So we can say that above 10 degrees it's almost entirely cyanogenic. So 10 degrees C plus, all plants cyanogenic more or less. And then from -4 to 10, it's just proportional. So it gets hotter. So from -4 degrees to 10 degrees, there are increasing proportions of cyanogenic plants. And we can say no cyanogenic below -4. So below -4 degrees C, no cyanogenic plants. And that's our temperature, that's our mean mean minimum winter temperatures. So where I put temperature there, that's what you're going to say, mean minimum winter temperature. And why is this? Well, that's because we're getting slugs. So at the warmer temperature, slugs are not usually active at temperatures below 0. So we're getting slugs above 0. So above 0 degrees C, mean minimum winter temperature, slugs are active. And this is a deterrent against being eaten by slugs. So our cyanogenic plants have a selective advantage as plants produce cyanide when damaged. So if you were a slug and you started munching on a clover plant and it tasted horrible because of the cyanide, then you'd either die or probably you'd start to taste a bit horrible, and you'd go and eat some acyanogenic plants instead, some tasty acyanogenic plants. So that's really what you're suggesting there. And for our acyanogenic, we are also kind of, you've got the trend here, so you can say you're mainly below, I know we're kind of repeating ourselves really, below -4 degrees C, mean minimum winter temperature. Now all clover plants are acyanogenic. And you can tell this story of the proportion gets less and less as the temperature goes up, for reasons that we've already described. Why have we got acyanogenic plants here? Well, they don't need this cyanide. It's no advantage to them because the slugs are inactive. Slugs are inactive. So no selective advantage for being cyanogenic. And there's also this is something that you might not get on first looking through this. Well, it tells us, you may have missed it, when the leaves of cyanogenic plants are damaged by slugs or exposed to low temperatures. The cell membranes are broken, releases cyanide. Right. So cyanide is actually an inhibitor of respiration. So it's a non-competitive inhibitor of the electron transfer chain. You might not have known that. But plants respire too, and so the cyanide would kill the plant. So actually, below -4, if it freezes and we get some cell damage, then those plants are going to die if they are cyanogenic. So there's definitely going to be none there. So we're going to talk about cyanide is an inhibitor of respiration, and it's a non-competitive inhibitor of the electron transfer chain. You could write that down. And if very cold, then cells are broken. In particular, the membranes are broken, releasing cyanide, which is toxic to the plant, as the plant respires. And so there's definite disadvantage to having this cyanide in very cold. There's no slugs, so slugs aren't a problem, so why produce it anyway? And if you do produce it, it's cold and it's going to kill you. So of course we get acyanogenic plants in a very cold environment. So 3 fields there. You might have found the first one a little bit easier. To get 9 marks, you need to be kind of confident in talking about all 3 areas. And that's the end. Lots of mocks done. Well done.